Hello everyone, we are Group 18. Our project focuses on optimizing a robotic manipulator system with three serially connected Revolute joints. The goal is to minimize energy consumption while maintaining precise and stable trajectory execution. To achieve this, we optimize design, trajectory, planning, and control strategies across three tightly coupled subsystems. The system is decomposed into three subsystems. Subsystem one is the mechanical system. Subsystem two is the trajectory planner. Subsystem three is the controller system. These subsystems are tightly coupled, both in data and constraints. For example, the mechanical subsystem outputs link inertia and mass, which affect the dynamic in both planner and controller. The planner outputs desired joint trajectories, which are used as input for the controller. This is the flowchart summarize the data flow between subsystems. For example, inputs like start and end waypoints feed into the planner, and all of this stays within the defined system boundary. Our modeling follows a modular strategy. We made several assumptions to the mathematical modeling establishment. Each subsystem is optimized using a tailored algorithm. For example, mechanical design uses a generic algorithm. The planner uses Cassetti and iPopt for nonlinear programming, and the controller uses fmincon with SQP. These subsystems are coordinated using the IDEA framework at the system level. We implement this in MATLAB using fmincon, with wrapped calls to each subsystem and custom visualization of the result.
So I will introduce about the subsystem 1 and what we have done since the interim report to refine the model, integrate with other subsystems, and finally make a difference. The input to the subsystem 1 is also the input to the entire system, as described before in the system level introduction. After the parameters are passed in, this first subsystem will calculate optimized link geometries and material selection and pass this data to the next subsystem as inputs. These are constraints for the first subsystem, which mainly focus on the material properties and preventing the links from failure in either ways. In this slide, we include the manufacturing constraint and workspace constraint, which also limits geometry from being too strange or exceeding the space limit. This is the objective function designed for the subsystem 1, and it's just a total mass with a couple of scaling weights. This slide describes the trade-offs between constraints and why we wanted them. The constraints are forcing the optimization procedure to give reasonable results within the bounded design range. When we take a look at the active status of the constraints, we can see a good balance between them. When it comes to the difference from our previous work, we can conclude that we changed the output format for better data analysis in subsystem 2, and we integrated another function to turn the geometry data further into a rotational inertia matrix. Talking about the mathematical modeling, we made the following assumptions to stick to realistic environments and easier simulation. Furthermore, we concluded the detailed steps in mathematical modeling for calculating the inertia, stress, and deflection. Now let's discuss about the optimization method. Same as in the interim movie, we still adopted the genetic algorithm and utilized MATLAB to solve the design problem. This method has advantage in this kind of NLP problems, and that's exactly what we want. And lastly, here are the optimization results. These results do not deviate from the results presented in the interim movie very much, because it's a sequence optimization in the system level, and this is the first subsystem. So most modification happens after the data was collected and how they are analyzed.
Subsystem 2 of the optimization model is the path planning subsystem. The inputs of the subsystem are the segment moments of inertia, masses, and lengths, as well as the start and end joint angles of the motion. The outputs of the subsystem are the joint positions, joint velocities, and joint torques, all of those parameterized as a discrete function of time. So below I will be presenting three different scenarios of robot motions to demonstrate the range of motions that this pathfinder can operate in. The first one demonstrates a lifting of the end effector from a low position to a higher position. As you can see, the joint angles represent a smooth transition from the start to end positions, as well as the capability of maintaining the velocities at both start and end to be 0. Here the motion is a inversion of the end effector at a low pose. Similarly, the motion is smooth and start and end velocities are 0. Here the motion is a bit more complicated, and it includes a rotation of the base joint while returning the end effector to its original position. Again, despite the working against gravity, we can see that the planner successfully plans the trajectory while minimizing joint torques and maintaining a smooth transition of joint angles.
So now we're going to talk about the subsystem 3 controller. So our optimization model focused on a single joint. We optimize a PAD controller to follow a given desired angular trajectory. So our inputs will include time-dependent rotational inertia and time-dependent external torque and desired angular position trajectory. And our output will be the RMSE between the actual joint position and the desired trajectory. The system dynamic follow the equation. The first one is where I of t is the time varying rotational inertia, q is angular position, and tau represent torque. The control law is discretized using the forward Euler method and is expressed as below. The third one would be the RMSE tracking, and the objective function J is defined as below.
So the optimization method we use for subsystem 3 is the MATLAB function fminCon with sequential quadratic programming algorithm. The objective of this is to minimize the root mean squared error function over the full trajectory simulation for each joint. The constraints we had on this model, we constructed the open loop transfer function, which ensured a phase margin less than or equal to 45 degrees. And then we set an actuator torque limit of 300 Newton meters, which is in line with real world motors. We set some bounds on the PID values so that they're within realistic limits. And then we set the max evaluations for each run of the program to 1000. So now some overall system-wide results. You can see the results from subsystem 1, which were fed directly into subsystem 2 to generate the following optimal trajectories for each of the 3 joints on our robotic manipulator. And then those were fed into subsystem 3, and you can see after going through the model dynamics, the tracking between the actual robotic manipulator joints and the optimal trajectories, along with their PID values and the root mean squared errors.
On this slide, we examine how individual key parameters affect system performance. For the mechanical subsystem, we vary the initial I. For the controller, the PID gain, and for the path planning, the maximum velocity. Each parameter was adjusted by plus or minus 20% from its optimal value. The plots clearly show that any deviation will increase or decrease, resulting in higher performance index, indicating degraded performance. Essentially, each subsystem is highly sensitive to its key parameters, underscoring the necessity of maintaining tight tolerance in design. Moving to the coupling analysis slide, here we explored the interaction between the pair of parameters. initial with PID gain, initial with maximum velocity, and the PID gain with maximum velocity. The 3D surface and contour plots reveal that when two parameters deviate simultaneously, the performance index J increases non-linearly, often more severely than the individual changes. This confirms that not only it is critical to control each individual parameter, but also to maintain their optimal relationship for robust and overall performance.
So now let's talk about the discussion and the future work. In the final stage of system level optimization, we link subsystem outputs such as torque demands directly to the controller optimization to jointly solve the entire system. Shared variables like torque limits and time discretization are aligned to ensure consistency. The model is then refined by incorporating realistic actuator dynamics such as saturation, late limits, friction, and backlash. To better match industrial conditions, we may also include flexible link dynamics or variable payloads. Lastly, trajectory planning is enhanced by adding obstacle avoidance and effector constraints or exploring time optimal and jerk limit paths for smoother motion and improved hardware longevity.